Thank you, Mr. Chairman, for a kind introduction. Good morning, ladies and gentlemen. Day number 3. It's an honor for me to start this day. It's always kind of challenging to get everybody awake this morning, so I will do my very best to accomplish that. As you already introduced, challenges and capabilities in software development for a fundamental-based simulation of on and offline simulation of steel making processes, metallurgical processes. So, what's in it for you today? What can you expect from that presentation? I will ramp up to the topic with a short introduction just to get you a feeling what I'm going to talk about today. Followed by some kind of background information that is related to fundamental-based modeling to metallurgical stuff. And later on, the main topic is the model library itself, which is our core component to solve the issues, or that we try to face the challenges that we have. And to sum it up, or to round the presentation, I will show you some results and installations that we made over the last, let's say one and a half year already now. So, let's start with a short introduction. You may be familiar with this application. It's Google Maps. Is that okay for you? Yeah. Okay, perfect. That's Google Maps. And actually this picture was the same thing that I saw when I arrived 2 days ago in Kiev. My first time in Ukraine. My first time in Kiev as well. So I was pretty lost actually, as you can imagine. And I just arrived at the airport. I was not pretty lost, but because I had a great transportation service, so thanks for that. No, but at the end, if you don't have any idea where you have to go, you just start Google Maps, type in where you want to go, and the problem is pretty much solved. But the most important part of this picture, the very point of the picture, is that small black and white dot on the airport of Kiev. Why? Because this point shows you exactly where you are right now. Because when you don't know where you are, at this very moment, you cannot predict where you want to go. So if you don't know where you are, you have no idea where you have to go. And this, ladies and gentlemen, this is what we as Inteco understand about modeling. Modeling helps us, or helps our customers, to know where they are just right now during the process of steelmaking, in terms of real-time simulation. So in every second or in every moment during the process, no matter if it's electric arc furnace, ladle furnace, or whatever, in every moment you perfectly know where you are, because modeling helps you to tell you where you are right now, and based on that situation, you can make a forecast and tell, okay, from this point of view, it's better to go in that direction or in that direction. So you can imagine it like that. Okay, let's go over to some background information. As I said, or as it is already in the title, fundamental-based modeling. What means that for us? That means that we try to build up every model that we used in our software from a fundamental-based, or from physics, chemical reaction, all these kind of things. So this is more or less the fundament of the models. And then to get the model working also for our customers, then we start with some empirical equations or whatever, or also some factors to tune it, that at the end it predicts the right value. But we can say, in general, all the models are based on fundamental physical concepts. Good morning. What does that mean? The holistic fundamental approach, process modeling, means for us, to sum it up, I just prepared this slide to sum it up. It just means 3 points for us. In every moment, we perfectly know the mass of the chemical composition of the steel, which is here X of I, where I is carbon, silicon, manganese, whatever composition your liquid steel has. We also know in every moment the mass balance of the slag composition, like CaO, MgO, and so on. And the third point is the temperature of the system. And with these 3 approaches, you can predict or you can say at every moment what's going on right now. So it's just these three things: the mass balance of the chemical composition of the heat of the liquid steel, of the slag, and also the temperature. This picture, I have no laser pointer unfortunately. I try to have one. Here is one. Perfect. Perfect. Okay. When it comes to modeling, we try, or this picture more or less shows that we start with a delta time. So that means it depends on, let's say, of the capability of the servers and so on, in which time range you can evaluate or recalculate the current state. Usually, most of the customers use 4 or 2 seconds. So that means these little dots, that means the recalculation of the online model will re-evaluate every 4 seconds depending on this picture here. You cannot do real-time modeling without the data from the shop floor. So the most important is that we get the real-time, the data from the shop floor, which is the equipment, our level 1 systems actually from Inteco. So this is directly connected to our modeling suite. So the input is the process data, process conditions. This data directly goes into our thermochemistry and thermodynamic model. And the result is every 4 seconds or 2 seconds, the result in each recalculation is a delta of mass of a chemical element. For example, if you think of the VOD process and you blow oxygen on the liquid steel, you're going to oxidize some elements. For example, first of all, aluminium, titanium, and last but not least, hopefully carbon. So in every 4 seconds we calculate this amount of carbon that we lost due to the oxygen blowing rate. And also the delta temperature. We saw yesterday also a ladle furnace model. When you arc the steel or when you heat it up, you have every 4 seconds you can predict perfectly how much delta temperature you will gain in each of these calculation cycles. You have seen this slide or this color thing of thermodynamic modeling and thermochemistry. Everything is related to thermophysical properties actually. So the most important thing, and this is actually what we are doing before we start to calculate a specific process like VOD or ladle furnace. In each step, we calculate the equilibrium conditions, and therefore we use in our model like the equilibrium constants, enthalpies of reaction, really important also for VOD processing modeling, interacting coefficients. The most important thing for calculating activities, because you can, for example, a desulfurization model highly depends on the activities of the slag and the chemical elements in the steel. And also, of course, the equilibrium conditions. Here is also some, for kind of background information, an example of the VOD process. What you see here is the difference between stoichiometric decomposition and kinetic decomposition. Because when you blow oxygen on the liquid steel, first of all, the elements get oxidized by just a stoichiometric approach, where the, let's say aluminium, titanium directly reacts with the oxygen that you blow onto the steel, and then when the system gets into a specific condition, then the kinetic approach leads over the stoichiometric approach. So, what kind of challenges do we have actually? The thing is that real-time modeling is an important thing. As I said in the introduction, it shows our customers where are you right now in the state of the process, or during the treatment of VOD, ladle furnace, whatever. But the same challenge we face with every customer, because no ladle furnace is the same, no VOD unit is the same, everything is like different, and so you have to adjust the parameters for your model that is like accurate enough. And this is why we have two approaches. One of them is online simulation. This is what I've talked about right now, to recalculate every 4 seconds the state of the heat. And the other thing is offline simulation. And offline simulation is for us really important because we try to simulate the same models that we use for real-time calculation. We try to simulate them offline so that the customers directly see what's going on with these parameters, how can we tune them, and then use this in the real-time calculation. So in general, we have two approaches: online real-time modeling and offline simulation. And to solve this, or to optimize this, we created an integrated model library. What means that? That means that we develop the models and use them in both approaches, for online real-time calculation as well as for offline simulation. In software development, there are some challenges coming up because offline simulation has totally different requirements, totally different needs than real-time simulation. You have to check the performance and everything because you have to recalculate every 4 seconds. Offline, there is no problem. You can just click on a button and simulate what's going on. So this is basically totally different things. And anyhow, we tried to have one model library integrated in both concepts. Why? Because when you simulate the process, for example, the VOD process, offline, and you tune some parameters, with this approach you can be sure that when you adjust these parameters, that the same code will execute it online. It's the same model, so you will have the same results. And this is the reason why everything is much faster during commissioning. And now I want to build up with you such a model library to show you how we solved this approach, or how it was possible to use it in both approaches. It's like a kind of Lego game. I don't know if you know Lego, these small little blocks. Starting with the fundament, as I